Hello again, everybody. Alright, section 4.7 is starting, and it's going to be involving something that you've done to a degree. We're going to take it to a whole new level. In this section, we're going to be solving exponential and logarithmic equations again. This will take place over 2 videos as far as the instruction goes, and we're going to focus this one on solving exponential equations. Now, this is going to work kind of similar to what we said before, where when you solve an exponential equation, you use a logarithm. When you solve a logarithmic equation, you use an exponent, but these are going to be more complicated than the ones that you used prior to now. Alright, so you got the idea of what we're trying to accomplish. All you need to do is see the examples, and here's the first one that we've got, which happens to be one that you would be able to solve learning what we know already, which I'd like to show you. But then I'd like to show you another option that you have that's going to make a lot of other more complicated exponential equations a little bit easier to take care of. Alright, so the term that has an exponent has a base of 12, and so what we said we could do to cancel out that base is we can just go ahead and take the log base 12 of both sides of the equation. And so I'm going to go ahead and do that right now. And of course, then the log base 12 cancels out with the 12, leaves you with x minus 3 is equal to log base 12 of 4.8. And then we could add 3 to both sides in order to get x by itself. So x is equal to log base 12 of 4.8 plus 3. Okay, but I need you to see an alternative way of solving the same equation. You don't have to, it turns out, pick a logarithm that has the same base as the exponential term has. You can pick any base that you want to. And you might guess that the most common choices for such a thing are a base 10 logarithm or a base E natural logarithm. And I tend to choose natural logarithm myself. If for nothing else, the ln is a little bit shorter to write than log. What we're going to do is we're going to take the natural log of both sides of this equation. So the natural log of 12x minus 3 is going to equal the natural log of 4.8. Now, a disadvantage seemingly to this is that 12 and the natural log don't cancel because the bases right there are not the same as one another. However, it doesn't prevent us from getting x by itself because we now know some properties of exponents that we didn't know before now that are going to allow us to get this exponent so that it's no longer an exponent. What we're going to be able to do is we're going to be able to take advantage of the power property, and we're going to make that exponent into a coefficient for the logarithm. So it's going to become then, the equation will become x minus 3 times the natural log of 12 equals the natural log of 4.8. Now to get x by itself, what we're going to do is divide both sides by the natural log of 12. That'll give us x minus 3 equals the natural log of 4.8 divided by the natural log of 12. And then we can go ahead and add 3 to both sides. So then, x will equal that same ratio that you see over there, plus 3. Alright, now in this example, I'm leaving my answer as an exact value, so we're not going to plug this into the calculator, although you know how to plug that into the calculator and round to 3 significant figures. Your homework problems will ask you to do each from time to time. But since I'm not changing this to a decimal, I need you to see that both these answers are equivalent. And so I want you to go back, or I want to go back over to the other way we worked the problem and show you that it is the same thing by using the change of base formula. That log base 12 of 4.8, you know that we can make that into log of 4.8. Well, you know what? I wanted to show you it's exactly the same. Let's use a natural logarithm. Since we can choose our base, it's the natural log of 4.8 over the natural log of 12 plus 3. Two ways of getting the same thing. Either choose the same base as the term that has the exponent, or choose whatever in the world other base you want to choose. Natural log, a good choice. Alright, next example. And in this one, here's where knowing that other method kind of comes in handy. We've got both sides of the equation having a variable as part of the exponent. And so how would you choose whether you use log base 6 or log base 13? Well, turns out you don't have to choose, although you could choose either one of those. You can also choose natural log, and that's what I'm going to go with here. Let's take the natural log of both sides. So that'll give us the natural log of 6 to the x plus 1 power is equal to the natural log of 13 to the x minus 3 power. Now what do we do from there? Well, what we're going to do is we're going to go ahead and use the power property on both sides of the equation so that we no longer have exponents or variables and exponents. So we'll have x plus 1 times the natural log of 6 equals x minus 3 times the natural log of 13. And this seems quite complicated. We've got a couple things that we're about to accomplish right now, and I promise in the end it works out quite nicely for you. We've got x's on both sides of the equation, and we can't just divide both sides by x minus 3 or anything like that. It's just not going to help us so much. What we're going to do is we're going to use the distributive property on both sides of the equation. We're going to distribute the ln of 6 on the left side. We're going to distribute the ln of 13 on the right side. So that will give us x ln 6. Always better when you multiply a logarithm by a value that you put that value in front. So I would never put the natural log of 6x without the use of parentheses anyway. Alright, and then the natural log of 6 times 1 is natural log of 6. On the right side, we're going to get x times the natural log of 13 minus 3 times the natural log of 13. Okay, now we still have the problem where we have x's on each side of the equation, but now we're in the instance where we can use subtraction to get them on the same side of the equation. I'm going to subtract x ln of 13 and get all the x's on the left side of the equation, and I'm going to subtract ln of 6 and get all the constant values. That is a constant value. I'm going to get all the constant values away from our variables. Alright, so x ln 6 minus x ln 13. It's going to equal negative 3 ln 13 minus the natural log of 6. Alright, two more steps here and we've got this. We're going to try to make it so that we've only got one x here, and the way we're going to do that is simply this. If both of the terms on this side of the equation have an x, we can factor out that x. Make this x ln 6 minus the natural log of 13 equals what was on the right side of the equation. And then we'll go ahead and use division, and we've got our answer. Looks pretty complicated, right? But if you follow the process, I think that you're going to be okay with it. Now, one thing I want to emphasize several times throughout this video is that sometimes you're going to have to leave your answer as an exact value. Sometimes you're going to approximate. This is an exact value. And then you can always use your calculator and approximate to 3 significant figures. Which gives you 12.3 in this instance. Alright, great. Let's try another one here. Same idea, we've got two different sides of the equation that each have variables. We're going to take the logarithm of both sides, natural log if you prefer, and go from there. I want you to try this right now on your own. Pause the video, then watch my explanation when you're done. Alright, so we're going to take the natural log of both sides, and then we'll pull out the exponents in each side of the logarithms as coefficients using the power property. Now we need to get every term that has an x on the same side of the equation. Notice there's no distributive property this time because, well, we're not multiplying by any sum or difference. Let's just bring both terms to the left side of the equation. Good so far? Okay, Now we're going to factor out x. And then all we have left to do is to divide both sides by whatever we're multiplying x by, this whole 5 ln 1/2 plus ln 5. Now this works out pretty nicely for us. If we divide 0 by that quantity, it's just going to give us 0, isn't it? So for that big old long equation that we had, turns out x is equal to 0. Not bad. It's true, isn't it? 1/2 to the 0 power is 1. 5 to the opposite of 0, that's still 5 to the 0 power. It's also equal to 1, right? Excellent. Next example. All right, same idea here. There's just going to be one added step. We're going to take the natural log of both sides of this equation. So let's go ahead and write that down. But what makes this one different from here is simply this. Since I have a product and only one of the factors has an exponent, I can't yet use the power property. I could only use the power property if this was the natural log of 3 to the x plus 2. But that multiplication right there makes that impossible. However, we can employ another property of logarithms that we've learned to make it so that we have a situation where we can use the power property. That is a product, isn't it? And can't you separate the logarithm of a product into the sum of two logarithms? So that's what I'm going to do here. We're going to make the left side of the equation into the natural log of 4 plus the natural log of 3 to the x plus 2 power. And we'll use the same basic idea for the right side of the equation. Now you ought to be able to see what's going to happen next. Now we can use the power property twice. This is going to start looking like a really long equation. I promise, if you pay attention, it's not all that complicated. All right, use the power property. You see it's getting pretty long, don't you? Now we're going to expand it even more. We're going to use the distributive property in these two places. So there's going to be 3 logarithms on each side. And here's the next thing that needs to happen. We've got exactly 2 terms that have a variable. I'm going to highlight those. We've got an x ln 3 and we've got an x ln 2. We need those on the same side of the equation. We need everything else on the other side of the equation. So let's bring the x ln 2 to the left side, bring this over here, and let's take both of these constant terms and move them to the right side of the equation. Alright, there's the 2 terms with the variable on one side. And 2 more things need to happen. We're going to factor out an x on the left side of the equation, as you know. And on the right side, we're going to start trying to make this simpler. I should have done this on a previous example and didn't, but that's fine. I'm going to try to make this all into a single logarithm. All these logarithms have the same base, don't they? It looks really messy with 4 of them, but let's use the power property and the quotient property a couple times. Now, watch exactly the way that this is done, because there's definitely some explaining to do on the right side of the equation there. One thing I did was I factored out a negative sign from these 2 logarithms here at the end. And you can see why I did that with the natural log of 4. So where in the world does 9 come from? Well, I used the power property as well. I made the 2 an exponent for the 3. 3 squared is 9. Alright, and then I've also gone ahead and multiplied 5 and 2 and made that the logarithm of 10. And now, all in one step, I'm going to multiply the 4 and 9 to get a log of 36, and then use the quotient property to make it the natural log of 10 over 36. And while we're at it, we might as well combine this natural log of 3 minus natural log of 2 into a single logarithm. So that would be the natural log of 3/2. Alright, we're finally at the part where we can get x by itself because it's easy to divide now. We'll have this logarithm divided by this logarithm. I'm going to write that as 5/18 by the way. Now if you understood that, you ought to be feeling pretty smart right now, shouldn't you? That's easily the most complicated looking equation that we've solved. But it's all about using those properties of logarithms that you understand. We're going to do one more example. Alright, let me write down the decimal value for this as well. Then we're going to do the one more example, and that's it for this video. There's that decimal approximation for you. Alright, well, here's another one. Now, I really would like you to try this on your own. It's going to end up being along the same lines of difficulty level as the previous example. Try it, please. check your answer afterwards. Alright, there's us taking the natural log of both sides. Next is using the product property to expand to get rid of the multiplication problems inside of the logarithm. Alright, and along with using the product property, I went ahead and used the power property as well. I took the liberty of putting the exponent for what would have been the logarithm as the coefficient for the logarithm there. And I did it also with the natural log of 4 to the x plus first power. Put the x plus 1 in front. Alright, now go ahead and use the distributive property here and here. Alright, so now we're at the point where we've got a bunch of single logarithms, and we need to get all the ones with the x's on one side of the equation, the ones without on the other. Let me highlight the ones with the x's. There, there, and there. Get those on the left side, put the other ones on the right side. And a couple more basic premises that we need to follow here. We need to factor out an x. And I think let's go ahead and do that. Just factor out the x. And I'm trying to set it up so that we can combine these logarithms into a single logarithm. And I will be doing that on the next step with this one, but I will go ahead and make this an ln of 9. Alright, and for our single logarithms, here you've got the product property and the quotient property that you're going to use. Let's do 8 times 3 divided by 4. 8 times 3 is 24. 24 divided by 4 is 6. So this side of the equation becomes x ln 6. And then on this side of the equation, these are all being added, these logarithms, so we're just going to multiply everything. 5 times 4 is 20. 20 times 9 is 180. So the natural log of 180 you'll get there. And finally, let's do the division. X is going to equal the natural log of 180 divided by the natural log of 6. You got that? I'm pretty darn impressed. And let's go ahead and write the approximate value just in case you ran into 3 significant figures. Now, if you're able to follow all of this, which I'm assuming that you can, some pretty bright students here, then you are showing yourself really truly worthy of being a Math SL student. This is the kind of math that I'm expecting that you're able to do. Really intense, where you have to pay attention to a lot of details. It's long, but it's all doable, isn't it? Thanks for watching. I'll see you with the logarithmic equation video next.